Okay, this is Acids, Bases, and Salts, Lesson 5. And tonight we're going to talk about the pH scale and different types of indicators. So let's start. The pH scale is based on the hydrogen ion. And it's a direct measurement of the H plus ion concentration in solution. So I want you to realize I'm going to put brackets around this, square brackets, because anytime we have square brackets like this around a symbol, that's equal to concentration. The pH scale is designed to measure how acidic or how basic a solution is. The concentration of the hydronium and hydroxide ions in a solution will determine whether the solution is acidic or basic. So remember, we discussed briefly that the pH scale ranges from 1 to 14. 1 being the most acidic and 14 being the most basic. And in the middle, you have a pH of 7. Like water. In an acidic substance, the concentration of your H plus is greater than your OH minus. In a basic solution, the concentration of your H plus is less than your OH minus. And in a neutral substance, the concentration of your H plus equals your OH minus. The pH scale is a logarithmic scale based on exponents of the number 10. So if I were to do log 10 on my calculator, I would get a 1. If I were to do log 100, I would get 2. And the log of 1 is always 0. And the log of 0.01 is negative 2. Now, I can find the pH of a solution by taking the negative log of the hydrogen concentration. So on my calculator, I would just do negative log, and I would take the H concentration and hit enter. So if I have a pH of 1 molar, HClO4, I would do negative log of 1, and I would get an answer of 0. pH of 0.5, I would do negative log of 0.5, and I would get 0.30. The pH of 0.01, I get a pH of 2. And if I do 12 molar, negative log of 12, I get a pH of negative 1.08. Now you might say, well, can pH be negative? Because then that would imply that it was less than 0. Actually, you can. HCl is a very strong acid, so sometimes really strong acids will have pH values of negative 0.96, negative 1. This one's a little bit more than that, negative 1.08. Just as bases can be slightly higher than 14 if they're extremely strong. For basic solutions, we find what's called the pOH, using the negative log of the OH concentration. What we need to remember is that pH plus pOH equals 14. So if I want to find the pOH, I would take the negative log of the OH concentration, and then to find the pH, as you can see, if I'm finding pH, I would just subtract pOH from both sides, and I get, these would cancel, and I would get pH equals 14 minus pOH. So the pH of a 1 molar sodium hydroxide solution. So remember, I'm going to take 14 and subtract the pOH. And I find the pOH by taking the negative log of the OH concentration. So here's my OH concentration right here. It's coming from NaOH. So 14 minus the negative log of 1 is going to give me 14. Because the log of 1, whether it's the negative log or the positive log, the log of 1 is always 0. A pH of 0.5 molar calcium hydroxide, I'm going to do 14 minus the negative log of, this is a typo, this is 0.5, so the negative log of 0.5. So please make that correction. It's not 0.1, it's 0.5. And then if we take 14 minus the negative log of 0.5, we get 13.698. So we can make this 13.7 for our pH. A pH of 0.01 LiOH, I would do 14 minus the negative log of 0.01. And I will get a pH equal to 12. And the last one, I have pH of 6 molar KOH. I'm going to do 14 minus the negative log of 6, and I get a pH of 14.78. Let's talk about what happens when we're changing pH units. Each change of a single pH unit is a 10-fold change in hydrogen ion concentration. When I go from a pH of 2 to a pH of 1, that's a 10-fold increase in hydrogen ion concentration because I'm becoming stronger. If I go from a pH of 2 to a pH of 3, this is a 10-fold decrease, or the hydrogen ion concentration is 1/10 of what it was, or is decreased by 1/10 of what it was at a pH of 2. So when we go from a pH of 4 to a pH of 5, so we're going from 4 to 5, we're becoming more basic because we're going closer to 14. So the OH concentration is increasing by basically 10 times. I'm becoming less acidic, and the H concentration is decreasing by 1/10. What happens when we go from a pH of 13 to a pH of 10? So we're going from 13 to 10. That's 3 pH units. So we're becoming more acidic. H concentration increases 1,000 times. Now, how do I figure that out? I told you each pH unit is 10 times. So it's like 10 times 10 times 10. So 1,000. It's becoming less basic, and the OH minus concentration decreases by 1/1000th. Where some common substances fall on the pH scale, and this is kind of a bad diagram. Here you can see this is lemon juice. You would be familiar with that. Vinegar, pretty acidic, okay, because his increasing acidity. Milk, which is kind of right there in the middle. Here's milk of magnesia, and ammonia and lye, so pretty basic stuff. This is your strong acids and your strong bases. I spoke to you about these the other night, the 6 strong. And notice how your strong bases are group 1. This is group 1, Li is group 1, Na is group 1, K is group 1, and Rb is group 1. And then all of these over here are group 2, Ca, Ba, Sr, and Ca. Strong acids and bases ionize 100%. I showed you the video animation about this the other night. So if I have NaOH solid, it's going to turn into Na plus aqueous and OH minus aqueous. NaOH is an Arrhenius base because it has OH minus as the only negative ion in solution. And we have HCl as a strong acid. It's going to turn into H plus aqueous and Cl minus aqueous. And this is an Arrhenius acid because it has H plus as the only positive ion in solution. This is incorrect information. Weak acids and bases have less than 5% ionization, partial ionization. And this should say a weak acid. Acetic acid, which is vinegar, actually is fairly weak in the realm of things. When it's a weak acid, we use a double arrow, okay? So you can either do this or this, whatever's easier, but it's a double arrow because very little of it ionizes. Notice we have one arrow to the right here because it's 100% ionization. It's going to go one way. All of the NaOH, all of the HCl are going to completely separate into individual ions. Where here you have H plus aqueous and you have C2H3O2 minus aqueous, but this reaction goes back and forth between the ions and the acid. And we have a weak base, ammonia, and in water that's going to form NH4 plus aqueous and OH minus aqueous. Remember, this is a good one from the other night. This also reviews the Bronsted-Lowry acid-base theory because here the H2O acts as a base and is an H donor. The H2O acts as an acid because it is the H donor. The NH3 acts as the base. It's the H acceptor. Ammonia and the OH in water, right here, here's ammonia down here. NH3, it has this lone pair of electrons. They battle for the hydrogen. So this N wants the hydrogen and the oxygen wants to keep its hydrogen. Roughly 1/10,000th times ammonia wins, generating a slight excess of OH ions, making the solution basic. Okay, we're going to talk about indicators. These are found in Table M, right under the acid and base tables that we talked about yesterday. So you know a little bit about what an indicator is. We've talked about phenolphthalein. We've talked about litmus paper. An indicator is a substance. It's technically considered a weak acid that changes color as a result of a pH change, so a change in the hydrogen ion concentration. Indicators are chosen based on their range for color change. And some indicators work better than others depending on how strong or basic a solution is. So we've already learned that phenolphthalein goes from colorless up until a pH of 8, and then it turns light pink from 8 to 9, and then really bright pink at a pH greater than 9, and we're talking magenta pink. Methyl orange turns red in a solution with a pH of less than 3.1, and it's orange between the ranges 3.1 and 4.4, and yellow in a solution with a pH greater than 4.4. Well, let's look at some of these. So here's my indicator table, and I want to just explain briefly how this works. So here's your range, 3.1 to 4.4, red to yellow. What this means is 3.1 or less, and the solution will be red. 4.4 and greater, the solution will be yellow. If I'm in the middle range, right here, greater than 3.1 but less than 4.4, my solution is going to be a combination of these two colors. Red and yellow makes orange. And this was the example that we were just referring to above. So, within the approximate pH range for colors, a mixture or blending of the two colors happens. This range is therefore also called the intermediate color range. So let's look at bromothymol blue at a pH of 6.4 or greater. Bromothymol blue, 6.4 or greater. Well, 6.4 is in this middle range. Bromothymol blue at a pH of 6.4. 6.4 is my middle range. Therefore, the blending of yellow and blue makes green. Bromcressyl green at a pH of 5. That's my middle range. A blending of yellow and blue makes green again. Phenolphthalein at a pH of 9.2. Phenolphthalein greater than 9 is going to be pink. And methyl orange at a pH of 3.9, that's in the middle, so it's going to be orange. All right, a couple of more examples and we're done. Methyl orange 6.0, well, that's greater than 4.4, so it's going to be yellow. Bromthymol blue at a pH of 2, it's less than 6, it's also going to be yellow. Phenolphthalein at a pH of 7. pH of 7 is going to be less than 8, so it's going to be colorless. Litmus at a pH of 6.8. So this is red to blue, so it's probably going to be in the middle there. It may be purple if it's a universal litmus. Bromcressyl green at 3 is going to be less than 3.8, so it's going to be yellow. Thymol blue at 7 is less than 8, it's going to be yellow. Methyl orange 2.2 is less than 3.1, it's going to be red. Bromthymol blue at 8.2 is greater than 7.6, so that'll be blue. Phenolphthalein at 10, that's a lot greater than 9, it's going to be pink. Litmus at 3.2, that's less than 4.5, it's going to be red. And Bromcressyl green at 6.2 is greater than 5.4, it will be blue. And thymol blue at 10 is greater than 9.6, that's going to be blue. Well, that's it for pH and indicators. Stay tuned tomorrow for an interesting lecture on neutralization.